What'd you say?
You're setting some high expectations here.
Yeah, this is a fun one. So 12.2 is what we're going to do is the chi-square test of independence. And since that wasn't recorded, this is one of my favorite lectures all semester because I think it's fun. Let's just open up a spreadsheet. So let me share this. What'd you say? The Chinese table? Oh, it's Greek. Greek, not Chinese. All right. Okay. So this is actually based on a true story. I'm going to keep the example simpler, but there was a lawsuit filed at the University of California at Berkeley. Based on this, we're going to just say that a university offers 2-degree programs, because we're going to try to keep this simple: electrical, engineering, and English. Admission is competitive, and women expect discrimination. Who's with me? Women, are you with me? Okay, because yeah, you got to deal with that all the time. All right. Is it fair to conclude discrimination? Okay. So we got males. This is a small college, small university. Females. And we got admit. And we got deny. And this is a tiny college, so we don't have that many students. 35, 45, 20, 40. Okay? So you are the statistician on hand. This is the data you're given. What do you think? What would be the first thing you'd probably want to do? We'll pick the women because, you know, you're the ones complaining of discrimination. Ashley, what do you think? Well, yeah, it'd be kind of hard to tell with just 4 cells. David. Oh, take off the light. So you guys are the statisticians here. You got this data. You got to be able to figure something out with it. What do you think? How would you prove, based on this table, that there might be some discrimination going on? Would be a simple calculation. Yeah, you could do the percent admitted, right? Let's just figure that out really quickly. So we got the percent admitted. In order to do that, we're going to need to get our totals, right? So let's get our totals. So if I add up that column, I got 80 males, and I got 60 females. So the percent admitted would be the 35 divided by the 80, which is about 43%, and about 33% of the women. So what do you think? Does it look like discrimination is going on? Jenna, do you think it is? You don't know? Look at the numbers. 43 versus 33, doesn't that seem like men are being admitted at a higher rate? Doesn't it seem like you should throw a lawsuit? No? Because you're a man, that's why. Doesn't that look like it? 10% higher admit rate for men than women. Doesn't that look like discrimination?
Depends on how big the college and the degrees are.
Well, we got 140 students, right? You guys aren't willing to say that looks like discrimination.
How big is the
Bunch of men are answering this. Ashley, doesn't that look like discrimination? Well, thank you. Finally. Bunch of Trump supporting men over here. All right. So let's file a lawsuit. They did that at University of California, Berkeley. It was much more complicated than this. But you know, that's pretty simple calculation, right? we can't be doing simple calculations like that. And this class has got to be harder than that. We got to do a hypothesis test. Okay? We'll find out in a minute here. Okay? All right, so the hypothesis test, now you guys know that we're going to be talking about a chi-square test of independence. This one also breaks the rule. I'll let you use a sentence on these. Okay? So I'll help you out here. What we're going to say here is that admission rate is independent of gender. Okay? So your null hypothesis in this case is always going to be independent. Independent means there's no difference, essentially. Okay? And your alternative hypothesis would be, now you would like to say dependent, right? But you know, we're statisticians, we can't say dependent. We're going to say not independent. Because, yeah, we don't want to say it's dependent. We can't prove that it's dependent, but it might not be independent, you know? Is there something biological at this university that allows men to get at the higher rate than women? Get admitted to the higher rate? It's probably not biological, isn't it? Okay? So anyway, so we're statisticians are anal. We're going to say not independent. We're not going to say dependent, okay? All right, so now, this is actually going to be very similar with what we did before, okay? So we're looking at our data here. We should by now be asking ourselves a question. Is this quantitative, categorical, or regression type of data? Who says it's quantitative? One. Who says it's categorical? A bunch more. Who says it's regression? Nobody? Who didn't raise your hand? One honest person. Okay, two. All right, so yes, it is categorical because we're saying you're either admitted or you're denied. Okay, what are the groups? Male and female. Okay, so don't mix up your categories with your groups. Okay, so it's categorical. So, what kind of a test do you think it should be? Should it be a chi-square, an F, a T, or a Z? Let's go in our regular order. Who says it's a Z? Who says it's a T? Who says it's a chi-square? Okay, because it's on the board, huh? Yeah. Who says it's an F? Okay. Why did you pick chi-square? Because it's on the board? Okay, what's the better reason? Because it won't be on the board on the test. Because I would not put it on the board on the test.
We're trying to see if an observed phenomenon differs from what
we expect. Okay, so let's talk about our chi-square tests for just a moment. How many chi-square tests do we have?
3.
This is our third one we're learning. So this is number 3, the chi-square test of independence. We've also got number 2 and number 1. What are those? Oh, sorry, the camera's not on there. There we go. Now we can see it on the camera. Okay, what are the other 2 chi-square tests that we have? We've got the goodness of fit, which we learned yesterday. And the normal. What was the other one? The first one. The what?
Pretty small, the average chi-square test.
Chi-square test of standard deviation. Okay, now by the way, these are both categorical. This one's quantitative. Okay, when it's quantitative, what's our degrees of freedom? It's equals n minus 1. When it's categorical, what's our degrees of freedom?
Row minus 1 times column.
Number of rows minus 1 times number of columns minus 1. Okay, so that quantitative categorical question, which I usually don't put on quiz as a test, is very important, but you should still answer, right? Okay. Now, here's the wrinkle today. Okay. The wrinkle today is you're going to have some sort of a table. It doesn't have to be a 2 by 2. In fact, here, I'll make this one a 3 by 3, just for fun. That's a big table. Anyway, okay. Now, this would be row 1, column 1, row 1, column 2, row 1, column 3, row 2, column 1, row 2, column 2, row 2, column 3, row 3, column 1, row 3, column 2, row 3, column 3. Okay? I'm not using that stupid S stuff anymore. You guys should change it when we do that. Okay? Now, here's the wrinkle on our expected counts. Expected counts. Okay? I'm going to give you, like, let's say that row 1, column 1. We're going to do this for every cell, depending on where you are. Okay? So if I'm talking about row 1, column 1, it's the row 1 total times the column 1 total divided by the grand total. Okay? Now you're going to do that for every cell where you are. Okay? So let me demonstrate what I mean by that. Okay? So here's what you may want to do. Okay? Now let's go ahead. We're going to call this the observed table. Here's what I would recommend you do on a chi-square test of independence. What you do is you will copy this table twice. Here, maybe we'll copy it across the top. Okay, this is going to be the expected table. And I'm going to blank out these cells. Now, I'm going to copy it again. And this is going to be the observed minus the expected table. So, and I should mention our formula that we learned last time, the chi-squared equals the observed minus the expected squared divided by the expected. We're still going to use that same formula just like we did on today's quiz. Okay? So that hasn't changed at all. But the main thing is this expected counts table. Okay? So we've already found the column totals. We're also going to need to find the row totals. Now, I should also mention something here. In fact, I'm going to erase that for a second. If you're not paying attention, this can get you in trouble, especially if you're using a larger than a 2x2 table. Okay? Now, you may be tempted to use this auto sum button, and you can. If you press that, it works, right? It's adding up the row. If you press it again, it adds up the row. Now pay special attention here. Watch what happens when I do it the third time. It adds up the column. Now, in this case, since it's a 2x2 table, it doesn't matter. But if you go larger than 2x2, that can cause you some grief and it'll mess up your calculations. So pay attention. It may be better simply just to do Control-C, Control-V, Control-V. Okay? That's the safer way to do that than using the button, because sometimes the button changes on you, and that'll be a problem. Okay, so we're going to go over here to the expected table. Okay, now here's where we're going to use this formula. Okay, where am I on my expected table? I'm in row 1, column 1. Okay, so here's what we're going to do. We're going to do row 1 total times column 1 total divided by the grand total. Okay? So, basically, here's what we're saying. If there was no discrimination going on, if the admission truly was independent of gender, I would have expected 31.5 males to get admitted. I got 35. I got a few more males admitted than I expected. The question is that significant? We're going to answer that question in a minute. Now, where am I at? I am on row 2, column 1. So here we go. I want the row 2 total times the column 1 total divided by the grand total. Okay? Now, I would have expected 48.5 to be denied. Only got 45 denied. Okay? Now, I'm in row 1, column 2. So I'm on the row 1 total times the column 2 total divided by the grand total. And I'm in row 2, column 2, equal to the row 2 total times the column 2 total divided by the grand total. Okay, does that make sense? Now, as we look at this, once again, let's look at the women. If there was no discrimination going on, I would have expected 23.5 women to get admitted. I only got 20. Okay, so maybe there's some discrimination going on. We'll see. Okay, so now we're going to use the same equation that we used Thursday. Okay, we're going to do the observed minus the expected. Okay, so this is here. So we're going to go, and parentheses are super important on this. You'll get it wrong if you don't use parentheses. The observed minus the expected squared divided by the expected equals the observed minus the expected squared divided by the expected equals the observed minus the expected squared divided by the expected and equals the observed minus the expected squared divided by the expected. Okay? Now, what does this mean? It means add them up. So I'm adding up this entire table here. So if I click auto sum here, I want to add up this table. Okay? All right, so I got 1.55971. Okay, let's talk about our degrees of freedom. What are my degrees of freedom? 2 minus 1 is 1, times 2 minus 1 is 1, 1 times 1 is, so I've only got 1 degree of freedom this time. Okay? All right, so this is my chi-square test statistic. Now I need to find my p-value. Okay, I'm going to pick on Samantha. Can you help me find my p-value? Chi-square dis right-tailed. Your sum you just got, which is 1.55. The degrees of freedom in this case is 1 degree of freedom. And I got a p-value of 0.211. Okay. That says do not reject, which means, what's my conclusion? There is not enough evidence of discrimination. Women, how does that make you feel? Okay, let's talk about this for a minute. McKenna, what do you think? Are you mad?
What?
Are you mad?
No.
No? Doesn't that look like there's discrimination going on? And this said there's not discrimination going on. And what would Mark Twain say? There are liars, damn liars, and statisticians, right? So, what's going on? Doesn't this look like we just created a conflict here? That's what they thought at Cal Berkeley too. And they said, because now the question is, which one do you believe? Do you believe the nice simple calculation that anybody can do in 3rd grade, or do you believe the more complicated one that all of you are struggling with in this class to learn? Okay, so here's what they said. They said, okay, fine. Maybe it's the engineering department that's discriminating against women. Maybe it's just one department, right? So they said, okay, fine. Let's find out here. Let's go to the engineering department and we're going to ask them for their admission rate numbers. Okay, so they go to the engineering department And they say that there's 30 men that were admitted, 30 were denied. What's your admit rate? It's 50%, right? Then they go over to the females. 10 were admitted, 10 were denied. What's your admit rate? 50%. Okay, well, it's definitely not the engineering department. They're fair, right? Must be the English department, since we only have 2 departments. So they go to the English department and they say, what are you doing? You must be discriminating, right? So in the English department, they had 5 men that were admitted. They had 15 that were denied. What is that admit rate? 5 out of 20 is 25%. Then they said there were women, there were 10 women admitted, 30 denied. What's the admit rate? 25%. So what do you think? Is there discrimination going on? No. Okay. Now let's go back to our first number again. Why does it appear that there is some discrimination going on when there's no discrimination going on? Okay. This is an example of what we call Simpsons Paradox. Okay. Simpsons Paradox says if groups are unequally sized, associations can actually reverse. And in fact, that is exactly what happened at the University of California at Berkeley. Now, in this case, we set this up so that you could see clearly there's no discrimination going on. But here's what's funny about Cal Berkeley. They actually did file a lawsuit. And the interesting thing was, it wasn't quite 50-50. Let's pretend for a minute that 29 males were admitted, 31 were denied. Let's figure out my totals. And so this will be, this is going to be this divided by that. And let's say that 11 were admitted and 9 were denied. And so when they went there, they said, oh, actually the women are having it better. Okay? And so that would be an example of Simpsons Paradox. That, yeah, there was discrimination going on, but it was in favor of the women. It was not against the women. And so when you break it down, especially when these are unequally sized groups. Now, part of the problem here is we've got 80 people in the engineering department. We've only got 60 people. 60 people in the English department. And the problem is because the engineering department is so much bigger than the English department, you can get associations like this. Okay? So let me go back to this question again. Which is the better calculation in this problem? Is it the nice simple one? Or is it the more complicated hypothesis test? Depends on whether you want to claim discrimination or not, right? Yeah, but the more accurate test is actually the independence test. Okay? And in fact, you'd probably say that a better conclusion would be it appears that admission is independent of gender, or it's not independent. Okay? So, okay, actually there's a couple other things that I want to mention really quickly. Let me write those on the board. Okay? Now, as far as, because I kind of skipped over these, the rules, the expected counts, no expected counts can be 0. Okay, that's rule number 1. Number 2, no more than 25% of, oh no, it's 20%. 20% of expected counts can be less than 5. Okay, so for example, let me go back to my table here. We're going to change this a little bit. Let's pretend, for example, that there was a 0 there. Can you do the hypothesis test? No, that breaks rule number 1. Okay. What if there was a 4 there? That's actually okay. Okay? Because it's the expected counts that we're looking at. Now the expected counts, instead of look at that 4, the expected count was actually 13. Okay? So that's okay. However, if this was a 4, would that be a problem? Yes, because 25% of your expected counts would be less than 5. So that would be a problem. Okay? Does that make sense? Now you're going to use bigger than just 2 by 2 tables. So anyway, I think that's all I got. That was right on time.
Will we be able to use Excel?
Will you be able to use Excel? Maybe, we'll see. If it's a nice simple one like this, I might get away with it. Yes.
So for this test that has just the 2 by 2, would you be able to use like 2 word or 2 population?
Oh, that's a really good question. Really good question. In fact, this needs to be recorded. He asked, could you have done a 2 population proportion on this? And the answer is actually, yes, you could. And in fact, the amazing thing about that is, I had a student that sat right in Trevin's seat last semester, and he argued with me about this. You'll get the exact same p-value. Okay? Now, the problem is, the independence test is usually used when you have more than 2 proportions, so 3 or more. But if you do 2, if you do exactly 2, you should get the same p-value whether you do a 2 proportion test or you do an independence test. So and we can demonstrate that tomorrow if you want. If it's more than 2, then it'll definitely be a chi-squared independence test. But a 2, you could either do it either way. Yeah. You want me to save that? You don't care about
I'm
that.
probably going to save mine, but
Yeah, I'll save it. All right. So quiz tomorrow is 12.2.